Good evening, dear participants. So today we are going to start our session 3 of second day of AICTE ATAL online FDP, which is on 7th January 2025. First of all, I would like to introduce our distinguished speaker, Dr. Pratyusha Rakshit. So it is my immense honor to actually introduce Dr. Rakshit. She was awarded her PhD Engineering from Jadavpur University, India in 2016. She is currently an assistant professor in the Department of Electronics and Telecommunication Engineering, Jadavpur University. Before joining JU, she was an assistant professor in ETCE Department, Indian Institute of Engineering Science and Technology, India. She was awarded gold medals for securing the highest percentage of marks in Bachelor of Technology in ETCE and among all the courses of Master of Engineering respectively in 2010 and 2012. She was the recipient of postdoctoral fellowship from Basque Center for Applied Mathematics, Spain, CSIR Senior Research Fellowship, Inspire Fellowship, and UGC UP2 Junior Research Fellowship. Her principal research interests include artificial intelligence and computational intelligence, evolutionary computation, robotics, bioinformatics, pattern recognition, fuzzy logic, cognitive science, and human-computer interaction. She is an author of over 80 papers published in top international journals and conference proceedings. She serves as a reviewer in IEEE TFS, IEEE SMC systems, neurocomputing, information sciences, and applied soft computing. So it is my immense pleasure to actually introduce Dr. Pratyusha, who is not only an outstanding scholar, an outstanding academician, but also a very humble and very ground, person. I think you must be very much, delighted to meet her personally as a resource person in this ATAL FDP. So I would like to hand over now the session to Dr. Pratyusha.
Thank you, Dr. Shaha, for this humble introduction. I do not know how much I meet this, as you have said, but I will try my best to fulfill the expectation of the audience with my current presentation. So a very warm evening to all of you, dear participants. And without any further delay, I would like to start my presentation today, which is a very significant research topic today. And most of you may be knowing the topic, that is evolutionary and swarm optimization. As the time is limited, I would just like to give the glimpse of the journey of evolutionary and swarm optimization techniques over the past 2 decades. So with this, I would like to start my presentation. Am I audible and visible to you all properly?
Yes, yes,
Thank you.
absolutely.
Okay, let's start. So as I have just said that today's my presentation topic is paradigm shift in evolutionary and swarm optimization. And first, going into depth of what I want to say, let's pick up a real world problem, because we before starting a research we should address the fact that why we are taking up that research. The research outlook should be like that. And before starting my presentation, I would request you all to please be a little bit interactive. That will actually help me to understand whether you are getting my things or like that. So just consider a real world problem. What's the problem? That is, there is a robot, and this is the starting position, and this is the goal position of the robot. The robot has two move from the starting position to the goal position following the shortest path, however avoiding collision with obstacles. So this is just the objective of the problem that the customer or the other party has given you, and you as an engineer or a management person, just I have come to know from last day presentation that some management people are also here. So you have to solve the problems from the words. Okay, so the objective of the problem in words is given like this. The robot has to move from the source position to the goal position following the shortest path. And as we all know from our basic mathematics that the shortest path between 2 points is the straight line. But here you see if the robot follows the straight line, it will obviously result in collision with obstacles. So the constraint is the robot has to avoid collision with obstacles. Now what is the job of an engineer? Whatever objective is stated in terms of words, that you have to represent or rather capture in form of a mathematical formula or function, and that function or mathematical model we refer to this as cost function or objective function. That I will come to later, but let's understand how I can transform the objective stated in the word to an objective function. So just consider currently my position is CT. T is the time. So current position is CT, and as I am showing everything in 2 dimensions, so it is having x and y coordinates, so xt and yt. So what is my objective from my current position? That what should be my next position? That is, I want to identify CT plus 1. So my objective from the current point is to identify the next position in such a way so that I can satisfy this objective. So the first part of the objective is follow the shortest path. So I should select CT plus 1 from CT such that the path length from the current to next plus next to goal should be shortest. So I should calculate the distance between the current to the next point that I want to go and the distance that I have to cover from the next to the goal position. So this is the total distance that I will cover if from CT I select CT plus 1. So this distance I need to minimize in order to ensure that I should follow the shortest path. Similarly, if you carefully see the second part of the objective, that is saying you have to avoid collision with obstacles. That is, you have to select CT plus 1 in such a way that the distance between CT plus 1 and the nearest obstacles should be maximized. So you see, the entire objective was in the form of words, but you have represented this in terms of functions. That is, you have to minimize this function, say f1, and you have to maximize this function, that is f2. Or rather, if I want to combine these two objectives, then I can say minimize f1 plus 1 by f2. Are you getting my point? Yes or no, please? Please respond, then it will be easy for me to understand. Participants,
Yes,
please interact. I can't listen as I can't see the online platform over here, so I just want to listen from you. Is it okay to all of you? Can I proceed?
yes, ma'am.
Thank you. Thank you. So first part is minimization, that ensures that the robot should be following the shortest path. The second part is the maximization, that should ensure that the robot should maintain maximum distance from the nearest obstacles. And together we form this objective. The minimization of this entire objective ensures both the parts of the objective. This is the thing. So obviously, as you see from the figure, from CT, there are so many CT plus 1 possible. So I have to select that CT plus 1 which minimizes this objective. And following this, the robot should be moving to the next position, right? Even then, as you see, that objective was stated in word, fine, then I have transformed it into mathematics, fine, I have solved the mathematics using certain techniques, fine, and then I am again executing the thing in the real world. So every calculation was done on a computer, but the robot is moving in the real world. So the solution that is given by the computer may not be always realized in the real world. And then you have to go in a loop. So where is the fault? That even if my computer is giving the solution, but my robot is not moving in a realistic way, the problem is with the objective function if. As I have just shown you in the example, the objective function f in the present case was formed as f1 plus 1 by f2 because f1 needs to be minimized and f2 needs to be maximized. But you have seen that using this objective function, your robot is not moving in the real world. Then what you can do? You can change the objective function as f1 minus f2. If you minimize f1 minus f2, that means you are minimizing f1 and maximizing f2. You can have other objective function formulations as well, f1 by f2. So there are many ways by which you can formulate your objective function, and the way you are forming your objective function will ensure that how realistically you can solve the real world problem. So here you are actually minimizing or maximizing one objective function to get the solution of the problem. And that's why the problem is called optimization problem. And most of you have solved optimization problem during your BTech curricula. The easiest example could be Newton-Raphson method. That is, you have been given one f of x, you have to find out the value of x for which f of x is maximum or f of x is minimum. So here I have just shown the problem in a real world scenario. So is, as I have said, suppose this is the objective function surface. As in the last problem, I have said that this is the, suppose, x coordinate of the robot, this is the y coordinate of the robot, and suppose this is the goal position of the robot. So as you have moved away from the goal position, the objective function value is high, and as you are going towards the goal position, you see the objective function value is decreasing. I am just showing it in a pictorial representation for you to understand how the optimization actually takes place. But initially, suppose you have thought that I am currently here. So if you are here, what is your objective function value? That this one. So what you supposed to do? You should move in a direction such that your objective function value should reduce, and like this. Are you getting my point? So in terms of mathematical optimization, we refer to this as direction of negative gradient. And this objective function surface is called, cost surface or objective function surface or fitness landscape. There are many terms which are used interchangeably. So that is fine. Then you can say, ma'am, we already have Newton-Raphson method and many mathematical optimization techniques are available here. So what's new? Why we are using AI techniques over here? Or where is the scope of AI? Where I am utilizing human intelligence? You see. When the objective surface, in the last problem, the objective surface was so smooth. Smooth means if you just take a cup or bowl and if you release a ball over the surface, the ball will surely reach the bottom of the bowl because the surface of the bowl is so smooth. But if the surface or the objective surface rather is like this, are you getting my point? This is ups and downs, ups and downs, ups and downs, and like that. So this is a true objective surface called ATAL function. Then what will happen? If I follow that negative gradient, suppose the objective surface looks like this. The person has started journey from here. So when it follows the negative gradient, it will fall over here and it will think, oh, I have got the minima. It will not understand that the true minima is somewhere here. It have to come above that and come over that niche, and it has to reach the true optima. That happens in case of ATAL function optimization if you try to solve it using classical technique. And you know what is this optimization surface is? It is same as this one, only when the surface is corrupted with noise, which is the most realistic situation. Because when the robot, just you consider the robot problem, we are always calculating the distance from the current position to next position, the current from current to the nearest obstacle. So the distance values the robot measures using what? Using the sensors, and the sensory values can really get contaminated with real world noise. The noise could be due to sensor characteristics, due to environmental problems. So the objective surface could be noisy, and if the noisy surface is like that, can you think that you can reach the true optimal solution? Yes or no, please? Students, sorry, audience, please. Please be a little interactive. It will be easy for me to continue. Hello, am I audible?
Yes, ma'am.
Yes, ma'am.
So do you think that in this case of objective surface, if I use the traditional optimization technique of following just the negative gradient, we can actually reach the true optima where we are having the minimum value? Yes or no? Yes or
No,
no?
ma'am. I think we will be able to.
Of course, we will be trapped at some false optima. We refer to them as local optima. Okay, I repeatedly request you to please be more frequently, interactive. Okay. So for this, what we have thought of, let's multiple solutions go for searching. For example, Anuradha is in some room of the college, and if I ask only one of you to find her in the entire NACC campus, how much time will it require? Obviously much longer time. But if I allow 10 of you to go in 10 different directions and search for Anuradhadi, I believe most of you will be able to find her out after a certain period of time. That is the main concept over here in evolutionary or swarm optimization. That is, I will not allow a single solution X to search for the minimum of X or maximum of X, whatever you say. Here in this slide, we are searching for the maximum. So I will ask solutions, or rather multiple agents, go and search where the maxima is, and after a certain number of evolution or cycle, we believe that most of them will be able to find it out. Even not, even if all of them cannot reach the maxima, they will be in close neighborhood. So that is the main concept of population-based search. Initially, if you consider Newton-Raphson or traditional optimization techniques, that was single agent-based search, but here it is population-based search, multiple agents-based search. So with this thing, with this concept, the new optimization algorithm that has emerged is called evolutionary optimization algorithms. So obviously there are much more mathematics involved in it. I just want to present it in a storyline manner. Okay. So just consider this picture. Okay. Initially, this is the objective surface. Now this objective surface which I am showing in the picture, for real world problem, this objective surface is not beautifully presented to you. Are you getting my point? For the single robot path planning problem, I may get an objective surface like this. But if I have say hundreds of robots, and in the last presentation by Dr. Parijat Bhumik, you have heard of multi-agent cooperation. So if there are so many agents, so many robots in a system, And if I want everyone to follow a shortest path from its own source to goal position, is it possible to draw the entire objective surface? No. Then you may ask, ma'am, how can you draw this objective surface? Just for your illustration. Okay. So, in case of robot path planning problem, I have considered minimization. Just for illustration purpose, here I have taken a problem of maximization. Okay. So, you just consider this is the parameter space or the subspace xy space, and this is the objective function value. So, how evolutionary optimization starts? It starts with random initialization of population of solutions. Okay, so I have randomly initialized, suppose 5 solutions, 1 2 3 4 5. Okay, so the first step will be first identify how good each solution are. How good means what is their objective function values. Okay, so I repeatedly am saying these solutions are actually on the subspace in the xy space. If I put their x and y value in the f function, then I will get their f value. Just for illustration, pictorial representation, I have presented the solutions on the objective surface, but actually they are on the xy surface. I believe you can understand. This is x surface, this is y surface. For every xy value, there is one f value. Okay. So this initial population of solutions is called parent population. They are the parents. Now, why the term evolutionary? There are two reasons why we are referring to this as evolutionary. The first thing is each parent will generate one child using some evolutionary technique like crossover or mutation, which happens in us also. Okay, so the red colored circles are the parents and the green colored circles are the children. So this parent has generated this child, this parent has generated this child, this has generated this child, and so on. Okay. Now, like we have identified how good each parent solution is, similarly, I will evaluate the fitness value of each child. That is, for each green circle, I will identify their objective function value or fitness value. Okay. Now, the second reason of evolutionary technique, why we are referring to this as evolutionary algorithm, that is each parent, that is red circle, will compete with its corresponding child, that is green circle, and the better solution will be promoted to the next generation. So I want the audience to be little interactive. So you see this parent, this red circle has generated this child, that is green circle. So if you consider this to be a maximization problem, that is more the fitness, better is the solution, then who is better, the parent or the child? If you just consider this picture, this parent has parent, so you see in the next generation the parent is still there. So you say, ma'am, what's the change then? The parent was there before the generation of children, the parent is still there. Okay, let's move to the next slide. This parent has generated this child. Who is better? This parent has generated
The child.
the child, you see. Similarly, this parent has generated this child. So every parent is competing with its own child. The better solution is promoted to the next generation. That is the principle of the survival of the fittest. Who is more adapting to the changing environment will be present in the generation. That is Darwin principle of survival of the fittest, which is followed over here. You just see, this was the condition before one evolution, and this is the condition after one generation. You see that the solution quality, you can say that has not improved too much, but has not deteriorated. Rather, they have moved towards the peak, that is towards the maxima of the fitness surface. Here I want the maximization, that's why I am saying maxima. So if you allow this circle to happen few generations for say 100 or 500, and if the objective surface is very complex one, then you can allow the generation to continue for 1,000 times. Then what you expect? That most of the solutions will gradually reach the true optima. If it is a maximization problem, the solutions will reach the peak of the objective surface. If it is a minimization problem, the solutions will reach the minima of the objective surface. So that's why here you see what advantages we have. That is, first of all, we are allowing multiple solutions to search for the global optima. It could be minima, it could be maxima. That's why I'm referring to this as optima. Second, our search is not biased with the initial population, which was in the case of traditional optimization. Like if you consider Newton-Raphson method, the initial solution x0 you will consider that will tell you how many iteration you need to reach the actually true global optimum. But here that's not the thing, because this initial population you are creating on a random basis. So that is the beauty of evolutionary optimization algorithm, that it can be used for any kind of real world problems. I do not want to advertise here, but I just want to say how many works we have done from our lab with collaboration with different people of different area. We have worked on bioinformatics, where the objective was like there are too many proteins in our in every organisms. So how the proteins are acting together, which two proteins will interact with each other, which do not, that can be predicted as an optimization problem. And we have seen that prediction of such protein interaction network has helped us to identify fatal interactive network responsible for Alzheimer's disease. Not only that, as in the last presentation you have heard of feature selection, which is an important part of brain-computer interfacing. There also we can use evolutionary optimization technique to identify what will be the optimal features to enhance the prediction accuracy. We have also worked on application of evolutionary optimization technique for healthcare management, for drone path planning, for cooperative multi-robot box pushing, and so on. So you can consider evolutionary optimization technique as a tool. It's not a particular problem, it's a tool. It can be used to any kind of application you can address, but what you have to identify, what is the objective of that particular application. Once you can state the objective properly in words, then your next job should be to transform that objective in words into particular function, that is called objective function. Once you have formulated the objective function, your 70% work is done. The 30% work is to select which proper evolutionary technique will work on that. So I believe till this, is it okay to all of you? Can I proceed? Is it okay to all of you? I do not want to make you bored, so I just want it to be interactive one. So people, if you can interact or say so.
Yes, ma'am, it's okay.
Okay. So I just want, thank you. I just want to give you a very simple example of evolutionary optimization technique, and in this domain actually my primary works belong, that is differential evolution. Okay, so here, as I have just stated, that first we should start with the initial population. So in differential evolution, this is a particular example of evolutionary optimization technique. The parent population is called target vectors. So after that, as I have said, that the parent population Z will generate one child U using some evolutionary technique, that is mutation and crossover. Then there will be a competition between the parent and the child to identify who will be the parent for the next generation. This T actually indicates the generation, and this cycle will continue until your convergence of the problem is achieved. So let's see in details what are the steps of this differential evolution and how it can ensure that yes, if you allow this algorithm to go for generation after generation, then you can achieve better quality solutions. So the first step is initialization. So uh, just consider the very simple problem of minimizing the sphere function. As all of you know, the sphere function is of the form x square plus y square. I am just considering the two-dimensional thing, that is the search space is having only the x value and y value, and for every xy value the f value is calculated using x square plus y square. Okay. So as you can see that this is a very simple problem where you can easily say that the optima is at 0. That is xy 0, 0. That means your f value is minimum, that is 0. But how we can ensure using this evolutionary optimization technique? So first step is to randomly initialize a population of solutions. Okay. So let us consider that I have initialized 5 solutions, that is Z1, Z2, Z3, Z4, Z5. And why this 0? Because this is the initial Z addition, that is indicated by 0, t equal to 0. So every solution should be within this search space, that is x dimension goes from -10 to +10, y dimension goes from -10 to +10. So suppose it is fully on random basis. So Z1 is initialized as 2 minus 1, Z2 is initialized as 6 1, Z3 as -3 5, Z4 as -2 6, and Z5 as 6 and -7. Fine. So what will be the, as I have said, the next step will be to identify how good each solution is. That is, you have to identify their objective function value. How? Just put this x, y value in F. So 2 square plus minus 1 square, 5. 6 square plus 1 square, 37. Minus 3 square plus 5 square, 34. Similarly, this is 40 and this is 85. So this completes the first step or initialization. That is, we have initialized 5 solutions within my search space, and for every parent solution, I have evaluated their objective function value. Okay. The next step is to generate the child using mutation and recombination technique. So the evolutionary technique that is actually used to generate the child from the parent gives so many options of evolutionary optimization technique. That could be differential evolution, that could be ant colony optimization, that could be genetic algorithm, that could be artificial bee colony, and there are many more to say. So here I am just discussing differential evolution just as an exemplar case. So let's move to the mutation. What happens in case of mutation? Every parent solution Z generate a donor vector V using this technique. Okay, that Zn, Zn and Zp are other 3 parent solutions, but which are different and which are not same as Zi. What I mean by that? Let us consider this. So as I have said that initially I had these 5 solutions, and now I want to generate one donor vector corresponding to Z1 using this mutation policy. So my mutation policy is saying that corresponding to Z1, if you want to generate one V1, select 3 vectors randomly from the existing population but excluding Z1. So what are the options in my hand? That is Z3, Z4, Z2 or Z5, and that should be selected on random basis. So suppose randomly the 3 solutions have been selected at Z4, Z2 and Z5. Okay, so if I just follow this equation, then what could be my V1? V1 could be Z4 plus scale factor F into Z5 minus Z2. So already we have the information of Z4, Z5, Z2 in our previous slide, and if I put all these values over here, here also vectorically I have shown what is happening, I will get my donor vector V1. Is it okay to all of you?
Yes, ma'am.
Okay, so you see, using mutation corresponding to every Z, I am generating one V. So Z1 is generating one V1, Z2 is generating one V2, like that. But no Z I is actually controlling VI. That is the beauty. This VI is generated corresponding to this ZI, but ZI has not participated in the equation. V1 is corresponding to Z1, but Z1 has not participated in the equation. Is it clear to all of you? Please, yes or no, please?
Yes, ma'am.
Then the question is why? Let's move to the next step, that is recombination or crossover. That is saying corresponding to every pair of Zi and Vi, we will generate one Ui, that is the actual child of Zi. And as you see, Zi is having two components, Vi is also having two components, so Ui will also have two components. Ui is the actual child of Zi. So what will be the components of Ui? The components can come from either V or Z corresponding on a condition. What is the condition? Condition is this one. This CR is called the crossover ratio. Corresponding to every component, I will generate one random value in between 0 and 1. And if this random value is less than crossover ratio, then the component will come from V. Otherwise, the component will come from Z. Is it right? Okay to all of you? Then I will give the example. Just consider this case. So for the first component of U1, suppose I have generated one random value and that is 0.96. And suppose my crossover ratio is 0.9. So here 0.96, that is the random value corresponding to the first component, is greater than 0.9. So whether my first condition or second condition is satisfied? First or second? Which condition is getting satisfied? Please. For every component of U, I am generating one random value. If the random value is less than the crossover ratio, which is 0.9, the component is to be coming from V, otherwise it should come from Z. So in this present context, the random value is 0.96, which is greater than crossover ratio, that is 0.9. So what do you expect? Whether my first condition is satisfied or the second condition?
Second condition.
Second condition is satisfied, and that's why the first component of Z will be contributed to U. Okay. But if you see the second scenario, suppose I have again generated a random value and suppose it has come out as 0.74, which is less than the crossover ratio 0.9. So which condition is now satisfied?
The first one.
The first one, and therefore the second component of U should be inherited from the second component of V. Is this technique clear to all of you? Yes or no, please?
Yes.
Yes, okay.
Okay. Now the question is, can anyone say why this is required like that? Crossover ratio, the CR value here is said as 0.9, that is, which is very close to 1. Suppose I have a scale like this and 90%, that is the crossover ratio, 90% of this scale is colored red and 10% of this ruler is colored blue. Okay. And now suppose I have asked you to close your eye and just put your finger on random basis on the scale for 5 times. Then maximum time, what color you expect to touch? Please, there is no mathematics, so anyone can answer. 90% is colored red, 10% is colored blue, and I have asked you to close your eye and touch randomly on the surface of the scale. So how many times, or not how many times, I mean, I'm just asking you maximum times which color you expect to touch, red or blue?
Red, ma'am.
0.1. So here, if I say that the crossover ratio value is set very close to 1, say 0.9, 0.95 or like that, and you generate some random value in between, then which condition is to be satisfied? That random value should be less than CR or greater than CR. Which condition should be satisfied maximum times?
Less than C.
Very good. So this first condition will be satisfied maximum time. So you will inherit most of the components from whom? V or J? V or Z? Just tell me.
V, ma'am.
V. So you see, child is inheriting, obviously, if otherwise condition is satisfied, child should get some quality from its parent, but in most of the cases, it is getting the components from whom? From the donor vector V. And if you carefully remember the mutation equation, this donor vector is not controlled by the parent. Donor vector is a separate thing. Okay? Why this has happened, why I am using this way of generating a child, that is the same thing we parents use to bring up our children. For a few initial years like 5 to 6 years or even 10 to 12 years, we may guide them properly. This is your home, this is the homely atmosphere, this is your family, these are the ways you should treat your parents, your grandparents or like that. But when the children are very much close to their friends, their school, their external world, where parents do not have any control, they inherit the characteristics, they imbibe the characteristics from the external world. So their characters are built by the parental influence as well as from the external influence. And the external thing, which is the donor vector over here, they are not being controlled by the parents. That's why if we go for generation after generation, our children are having more new characteristics, and they are more adaptable to the changing environment rather than us. We are more adaptable than our parents or grandparents, and our next generation will be more adaptable than we. The same thing is imitated in differential evolution. And the last step, that is the selection phase, is very simple. That is, you have a parent Zi, you have a children Ui, both at the same generation T. Now for the minimization problem, we calculate their F value, and if your child objective function value is better than the parent, then in next generation the parent will be the child. So if I follow the same thing over here, your Z1, you remember what was your Z1? I forgot. Your Z1 was 2 minus 1. So the objective function value was 4 plus 1, 5. And your child is 2 minus 4. That is 4 plus 0.16. That is objective function value 4.16. So for the minimization problem, you see the child is better than the parent. And that's why in the next generation, that is Z11, the current child will be promoted as the next parent. In this way, our generation is improving. And if I allow this iteration to go for, it is the result after first iteration. So it's like that. You see, this is the 5 parent populations. They have generated these donor vectors, and from them we have generated the actual children. Now every parent will compete with the child, and the better one will be promoted to the next generation as the parent. So here you see Z1 was 5 and U1 was 4.16. So that's why U1 was generated to next generation. But if you see the fourth case, Z4 was 40, its child U4 has an objective function value quite high, 120.64. So the parent minus 26 is still remaining as parent for the next generation. So you can ensure that if we go for generation after generation, my population may not get very good, may not get better, but it should not deteriorate. That is the principle of the survival of the fittest. That is the principle of evolutionary optimization, and differential evolution is one simple example of this one. I'm saying the word simple, but it has tremendous capability to solve real world optimization problems. So how much time? It's 7 almost. I should not discuss much more on this technique. So if you say that it's okay to all of you, then I will proceed to the actual paradigm shift of evolutionary technique. Is it okay to you all, please?
Ma'am, I have one question.
Yes, please.
So
I
all
can
these,
see you. So please just tell me your name, please, and then I can continue.
yes, ma'am, I am Subrata Pandey from NIT
Yes,
Durgapur. I am
yes.
a PhD research scholar. So
Okay.
all these optimization problems are dependent upon random number generators. So we cannot really reproduce the random number generator numbers. So suppose I am submitting one paper. So how do we, like the reviewer, believe that okay, this paper is telling the truth? Because in the next paper, suppose there are two comparative analysis of two different optimization algorithm. One is saying this A is better, another one says B is better. So how do we like really believe that which one is better? Because
So
it's
Shubrata,
really
I
random in
should
nature.
say, as you were saying that from the core of optimization things, I should say there is a theorem which is called no freelance theorem, NFLT. Okay, if you have a group of problems and your algorithm A is performing better than B on certain problems, then there must be certain problems where B should be acting better than A. Okay. You cannot say that A is better than B in all aspects. Only for a particular application you can select that yes, my algorithm is performing better than this algorithm. So
In
obviously,
in
as we
that
have,
case also, ma'am, if I run like 10 times, so this time like 7 p.m. today, it is giving that optimization algorithm A is giving better result, but 8 a.m. Tomorrow, it is the optimization algorithm B is giving better result. So how do we really believe on this competitive
no,
analysis?
no. There are many things to say on this. I do not know whether I should answer this after the session or not. Let's take just 2 to 3 minutes break here to discuss about this. That first of all, if you have one benchmark function f and you have two algorithms a and b and just running one time on f, you cannot say that a is better than b or b is better than a. There is statistical test which you have to undertake. That is, for the function f, you have to run a or b minimum 25 times. I mean 25 runs are required. In each run there will be 1,000 generations. I think you are getting that.
Yes,
So
ma'am.
for algorithm A, you are getting f value 25 times. For algorithm B, you are getting f value for 25 times. So in this 25 cases, in some cases A has performed better than B, B has performed better than A for some cases. Okay. Now using these 25 sample values, you have to undertake t-test or Wilcoxon rank-sum test, which are the non-parametric statistical test. And that statistical test will tell you whether there is significant difference in performance between algorithms A and B. If yes, then you have to identify what is the median values of this objective function values for A and B after the 25 primes. Are you getting my point? So suppose
Yes, ma'am.
median values or average values, whatever you say. So suppose the average value of A is better than B. Then also you have to test the Wilcoxon ransom test or t-test to identify whether that betterness or superiority is statistically significant or not. In evolutionary optimization, I think you were actually working on that. That's why you were asking. That is, it is very important to identify whether the result is statistically significant or not. So statistical test is the only thing that could be conducted over here.
Okay, ma'am. Thank you.
Thank you.
Understanding.
Okay, so I had many things to say over here, but I think time is less and I cannot cover the paradigm shift. So I'm directly skipping. Oh my God, it is not here. I'm not getting. Just a minute. My sharing is stopped, I think.
Yes, ma'am.
Okay. না আবার
Ma'am,
এসছে।
just check.
হ্যাঁ, দাঁড়া এক সেকেন্ড। Are you all getting my things? Then it will be, I will be very happy to continue. From beginning করে ফেলেছি, I'm very sorry. কোথায় ছিলাম? আমি একটু স্কিপ করে যাচ্ছি কারণ আমি প্যারাডাইম শিফটটা বোঝাতে চাইছি। Just a minute. Multi-objective. Is multi-objective evolutionary optimization visible to you all?
Yes, ma'am.
Okay. So till now we were dealing with single objective. We have a single objective. Now we move to the multiple case. Then you can say, ma'am, in robot problem we have two objectives. That is minimizing the distance covered and maximizing the distance from the obstacle. So we have two objectives. That is also multi-objective. No, because these two objectives are not conflicting in nature. You can simply add them, f1 plus 1 by f2, f1 by f2, f1 minus f2, or if you want to maximize, then it could be f2 by f1, like that. There are many ways. That is simply you can combine them. But what happens if the objectives are conflicting in nature? Just see the example. When you are going to buy a car, you want the material of the car to be like that, the accident should be, meaning accident rate, possibility of accident should be less. But if such material is provided for your car, then the cost should go high. No, but you do not want to expend more. So you want to reduce the price, you want to reduce the possibility of accident. So when you are having such conflicting objectives to play, then we are having the new era of evolutionary optimization technique, that is called multi-objective evolutionary optimization. Okay, and here you see, if you consider this red circle, here you see the possibility of accident is very less. If you just see its f2 value, then it's f1 value, the possibility of accident is very less. But if you see its f2 value, its price is quite high. If you see this solution, its possibility of accident rate is very high, but its cost is very less. So we say that this solution and this solution, they are equally good. No one is better than other. Or in terms of multi-objective evolutionary optimization, we say these two solutions are non-dominated. No solution is dominating other. So if you just see this set of solutions highlighted by yellow color, all these solutions are non-dominated. No one is better than other. And we refer to this set of solutions as Pareto front. As time is limited, so I am saying many more terms. So if you find it difficult, please stop me and ask me what terms I have said. That is called Pareto front. The set of equally good solutions in multi-objective optimization is called Pareto front. Similarly, you see this is another Pareto front. Similarly, you see this is another Pareto front, because in every Pareto front the set of solutions are non-dominated. The set of solutions are equally good. But if I now ask you, this is suppose Pareto front A and this is suppose Pareto front B, which Pareto front is better? I remind that I want to minimize the cost, I want to minimize the possibility of accident. So if I ask you whether the Pareto front A is good or Pareto front B is better, which one is better? From the graph, it's very easy to say, please. I want to minimize the cost, I want to minimize the possibility of accident. Which Pareto front is better? Please. Excuse me, am I audible?
Yes, ma'am.
Yes, please say me. I want to minimize the price as well as I want to minimize the accident rate. So based on that, which one is good? Pareto front A is close to the origin or Pareto front B is close to the origin? Bolo?
A, ma'am.
A, because Pareto front A is really close to origin means me. I want to minimize both of these. I want to minimize the price. I want to minimize the accident rate. So obviously Pareto front A is better than Pareto front B. So in terms of multi-objective evolutionary optimization technique, we say Pareto front A dominates Pareto front B. When we have the equally good set of solutions, we say they are non-dominated. But when the equally good of solutions in one front is better than the equally good of sets of solution of other front, we say one front is dominating other front. Is this concept clear to all of you? Yes or no, please?
Yes, ma'am.
Okay. Then I proceed to how this non-dominated sorting. What is the basic principle of multi-objective evolutionary technique using this concept of non-dominated solutions? So, in single objectives, what happens that a parent population is there. It generates a child population. Now each parent compares with each child to identify who is better. But here the thing is different because it's not a case of like single F value. That is, I have got mathematics, I have appeared in mathematics. My baby has also appeared in mathematics exam. Now I should compare only my maths value with his maths value. No, that is not the case. I have appeared in maths, I have appeared in physics, I have appeared in chemistry. My baby has also appeared in 3 subjects. Now there's a multiple comparison thing. So that is why what we will do, we will merge the entire parent population and the child population. So in parent population, suppose I had 5 solutions. So every solution has generated one child. So in child population also I have 5 solutions. So I will generate one merged population where we will have 5 plus 5, that is 10 solutions. Just a minute. Sorry. Now, as this slide says, from this merged population, we will execute non-dominated sorting to identify the Pareto fronts. Pareto fronts means that is in Pareto front 1, whatever solutions will be there, they are equally good sets of solutions. Pareto front 2, they are also equally good set of solutions, but poor than Pareto front 1. In Pareto front 3, whatever solutions will be there from this, they are equally good, but they are poor than PF1 as well as poor than PF2. So this is the ranking of the Pareto fronts. But as you have seen that in parent population we had 5 solutions, in child we have another 5, so altogether 10. So when we have identified the Pareto fronts, we are dealing with the all 10 solutions. But in next generation, I can allow only 5 solutions. So I have to disregard this part. It is easy to disregard this Pareto 4 and Pareto front 5 because they are going beyond 5. But what about Pareto front 3? Any doubt? Okay. So what about Pareto front 3? I have to partially select good set of solutions from them because in Pareto front 3, whatever solutions are there, they are equally good. Then how can I identify that who are partially better? For this, we have second round of sorting, that is crowding distance. I will come later. And finally, we have this parent population for my next generation. So obviously the question will be how I am generating this Pareto fronts and then how I am selecting this crowding distance. Okay. The first thing is how the Pareto fronts are created. Just consider that initially I have the 4 parent solutions Z1, Z2, Z3, Z4 and I have 2 objectives. F1 and F2. And I have given their value 12, 7, 15, 8, 17, 7 and 11, 5. Now every parent has generated one child and hence we have a child population of 4 solutions, that is Z5, Z6, Z7 and Z8. And I have tabulated their objective function values as well. Now I have to separate them into different Pareto forms and just consider, let us consider that we have to minimize both F1 and F2. So how to proceed? And I again request you to please be interactive. It will be easy for you to follow that how this non-dominated sorting takes place. So I should start with Pareto front 1 and without thinking anything, I should place the first solution Z1 in Pareto front 1. Okay. Now, the concept is I will compare all solutions from the population with the solution in my Pareto front 1, and if I find that my Z1 is dominated by any solution here, I will pick up Z1 and I will allow the dominating solution to enter PF1. What I mean by that? Let's start with the comparison. So I will compare now Z1 with Z2. So if you have compared Z1 with Z2, you see F1 value of Z2 is greater than F1 value of Z1. F2 value of Z2 is also greater than F2 value of Z1. So who is dominating home? I want both of them to be minimized. F1 should be minimized, F2 should be minimized. So I say that a solution is dominating other solution if F1, F2 both are less. So here who is dominating home? Who is
Z1
better?
is dominating Z2.
Z1 is better than Z2. Z1 is dominating Z2. So that means Z2 cannot enter PF1. Fine. So I should now compare whom? Z1 with Z3. 17 is greater than 12. Z7 is equal 7. That means Z1 is still dominating Z3. So Z3 cannot enter PF1. Now I compare Z4 with Z1. You see 11 is less than 12. 5 is less than 7. So who is dominating whom, please?
Z4 is dominating Z1.
Very good. Z4 is dominating Z1. That means Z1 should go out of Pareto front 1 and Z4 should enter PF1. Now I should continue comparison with Z4 with Z5. So if you compare Z4 with Z5, 9 is less than 11, 6 is greater than 5. Who is dominating whom? Here one objective is less, one objective is greater. That means they are non-dominated. They are equally good. And that's why Z4 and Z5 both will enter Pareto front 1. Is it okay to all of you? Yes or no, please?
Yes, ma'am.
Yes, ma'am.
Okay. Now the next solution, that is Z6. Now whenever we will go for the next iterations, I should compare with both the residents of Pareto front 1. If any one of them is dominating, I cannot allow new solution to enter. For example, compare Z6 with Z4. So 13 is greater than 11, 5 is equal to 5. So who is dominating home? Bolo? Z4 and Z6. Z4 is dominating Z6. So no way to compare Z6 with Z5 further because I have already decided that Z6 cannot enter PF1. Fine. So you should go for Z7. So Z7 with Z4, you see 12 is greater than 11, 8 is greater than 5. That means Z7 is dominated by Z4. So again Z7 cannot enter PF1. Then go for Z8. 7 is less than 11 but 7 is greater than 5. Who is dominating whom? Z8 and Z4. Who is dominating whom? It is written, so please say.
Equal, ma'am, because
Equal means they are non-dominated. So here we have a possibility that Z8 can enter PF1. To ensure that, what I have to do, I have to compare Z8 with the another resident of PF1. Who is that? That is Z5. So you see 7 is less than 9 and 7 is greater than 6. That means Z8 is also non-dominated with Z5. Okay, so that means Z8 is non-dominated with both the residents of Pareto front 1, and that's why Z8 can enter Pareto front 1. So you see, you have started with a blank Pareto front 1. You do not know that who will be the residents of Pareto front 1. You have selected the residents of Pareto front 1 based on the non-dominating criteria. That is called non-dominated sorting. But you see, still we are having the remaining solutions over here. So we will follow the same procedure to generate Pareto front 2, and if I follow this procedure, we will find this. Again, we are having 3 solutions remaining here. So we should go for selecting Pareto front 3. And if I follow the technique, we will see that these 2 solutions will be coming here. So see, till now we have one solution over here. So we will go for selecting Pareto front 4 and this will come here. So this table is now fully empty and we say that my non-dominated sorting is complete. So in case of non-dominated sorting, 2 things you have to remember, that you do not know how many Pareto fronts will be there a priori, who will be the residents of Pareto fronts a priori. Both you have to identify using the concept of non-dominated sorting. So as you have said that there were 4 parent solutions and 4 children, and here you see all are jumbled up. So in the next generation, you can pass only 4 because the parent population size is 4, but that means in next generation you can pass only 4 solutions. So you see, the best Pareto front is PF1. Here we have 3 solutions. We can simply pass them. And PF3, PF4 we cannot pass, fine. But in PF2 we have 2 solutions and there is only 1 room left for the next generation because 3 have been occupied by PF1. So only 1 solution can be passed from PF2. Who will be that? Because these 2 solutions are equally good. Are you getting my point? So when I have to select good solution or better solution from a set of equally good solutions, then I have to use a concept that is called crowding distance. What is that? Here you see these solutions are equally good. That is, if you want to minimize F1, the F2 is increasing. If you want to minimize F2, then F1 is increasing. So they are equally good. So for every solution, I am measuring a hypercube like this. That is, for the ith solution, I am calculating F1i plus 1 minus F1i minus 1 plus F2i minus 1 minus F2i plus 1. Okay. So that is called crowding distance. That you can just simply say that the area of the hypercube gives you an idea of the crowding distance of a solution. So all these solutions are equally good. Among this set of equally good solutions, you have to select a better solution. Then I will calculate this crowding distance, and the solution who is having more crowding distance will be given the priority. Okay. Now the question is, can anyone say that why more crowding distance is important from this figure? Why crowding distance? I mean, from this figure, can anyone say that what crowding distance is actually providing us? What information is being provided by the crowding distance? The word itself is saying that it is giving us the idea of crowd. You see, if the crowding distance is less, that means the solutions are very close to each other. And if the crowding distance is more, that the solution is situated in a very isolated space. That means the solution is having certain unique characteristics, though it is equally good with other solutions, but as it is in an isolated place, that means it is having some unique characteristics and I should save that solution for my next generation. But if I have 2 to 3 solutions whose crowding distance are very less, that means they are very close to each other. So I just can select any one from them. That is not a problem. But if I have a solution which is having a high crowding distance value, large crowding distance value, then it indicates that I am situated in a lonely space. Though I am equally good with my fellows, but I am having some unique characteristics. Please save me for my next generation. So that's why when I have to select quality solution from equally good set of solutions, I have to give priority to the solutions with higher crowding distance. So this is all about multi-objective optimization. The time is not there. I just give you a very small ongoing research that I am currently undertaking with my PhD scholars, that is many objective. This non-dominated sorting, crowding distance based sorting, everything works well when the number of objectives is less than 3. I think I should, okay, fine. Continue this. But when the number of objectives is greater than 4, then this technique does not work. Why? Suppose if I just say for my last semester there were 6 subjects and 5 students. So for not 6 subjects, suppose 2 subjects are there and I have 5 students. So just I have shown you the example of non-dominated sorting. Using this non-dominated sorting, I can identify who will be equally good solutions. I mean students who are better, who is worse. It's very easy. But suppose now if I ask for the same set of 5 students, I will identify who is better and who is worse based on their marks obtained from class 1 standard. Class 1, 2, 3, 4, then 10 standard, 12 standard, BTech, Masters, PhD and so many things. So what will happen? So marks means what? That objective function values f1, f2, f3. So here we will be having 100 of objective function values for all these 5 students. So what will happen? All 5 students will be identified as non-dominated, because in nursery or in KG, obviously you may find that the first student was better than the second student, but the scenario may get fully reversed during their PhD coursework. So when the number of objectives are increasing, and that is beyond 4, what happens that most of the solutions will be declaring themselves as non-dominated. All will try to occupy Pareto front 1. That is the scenario of many objective optimization, where we cannot apply the simple technique of non-dominated sorting. And it is a fully ongoing research. What we have thought of, that is, we will individually optimize each objective. Suppose there are n objectives which is greater than equal to 4, and then we will allow certain policy which is called migration of population among the solutions to identify, I mean, just to whisper, see, I am performing better here. Do you need my help? Then I can go to your objective surface to help you optimize that one. So this is a kind of ongoing research we are trying to do, which is bypassing the traditional multi-objective optimization technique based on non-domination criteria to solve many objective optimization. So obviously, as time is very limited, I should stop over here, because I should have certain time to take some questions from you. as well as our next resource person. I don't know whether Anishadi has already joined. She is a wonderful speaker and she is having, I believe, a very interesting topic to present to you. So it's just a time to take questions from you. If you have any problem, any doubt, please tell me. So this is a paradigm shift, I should say in a nutshell, that initially we have the traditional optimization, then evolutionary optimization has come to play. Then from there we have the multi-objective optimization, then right now many objective. And apart from that, there are many things like noisy objective optimization, that the objective function has become noisy. Then how to identify what is the true objective function value and how to identify the true solution of a problem. Then we have the dynamic optimization problem. Just you consider the depth of sea beach. I mean, obviously the depth of the sea is always changing over time. So if we have such kind of dynamic scenario, then how to identify what will be the solution at that current instant of time. So there are many more things to say. Obviously time is limited, so that's why I have just given a very short glimpse of the current researches that are going on in the era of evolutionary optimization. So if you have any question or doubt, I will be very happy to answer that.
Dr. Pratyusha, I must say that is a very engaging session we all have, and we love to listen from you about all the optimization techniques on what you are working for. And it is a exactly a very strong collaboration with you and your team and your lab, from where the participants will get an insight. And obviously, I must say that the participants will be, very much delighted to listen to you and your work and your knowledge sharing.
Thank,
So I
thank you
would
very
like
much.
to, yes, I would like to actually focus on that, this Dr. Pratyusha Rakshit is very much a significant and promising researcher whose session actually dwelled into the significant advancement in evolutionary and swarm optimization techniques, and how you are discussing that these methods, which is inspired by natural processes and collective behavior, are being adapted to solve very much complex problems, I can say, in various fields, including engineering, finance, and logistics, and even if in management field also. So basically, I thank you for giving us the opportunity to actually to hear from you and to be with you and your in such a busy schedule, so that we can collaborate in this ATAL FDP program.
Thank
So
you
a
so
big
much,
thank you for
Dr.
from my
Shah,
side.
for actually allowing myself to get engaged over here. And thank you, all my participants. Thank you so much.
Thank you, ma'am.
Okay, dear participants, so we are taking just 2 minutes break to, introduce yourself to the next session, because our next session resource person is just here with us. I'm just taking 2 minutes break. And one thing I just want to, share with you, you just please, on your camera, so that we can take a screenshot for the ATAL FDP attendance. And if we have Dr. Pratyusha with us. for 2 to 3 minutes, participants. Please on your camera so that we can take the screenshot. Thank you so much. You can switch off your camera and just give us 2 minutes break to actually process this recording of the session 3, and we will be rightly back for the session 4 as well. Thank you so much.